In this video, I will show you how to find the resultant vector when you have two vectors that are acting together and neither of them are the cardinal directions north, south, east, or west. I will show you how to use my patented four-step process to solve this and my very special graphic organizer technique. There's no patent or copyright. I'm just kidding about that part. So, for number 4, radiology technicians Mary and Joseph are moving a patient on an MRI machine cot. Mary is pushing the cot with a force of 120 newtons at 55 degrees with the horizontal, while Joseph is pulling the cot with a force of 200 newtons at 40 degrees with the horizontal. What is the magnitude of the resultant force exerted on the cot? Okay, so first of all, just the basic idea is that we have this cot, all right, like a bed on wheels or something. And Mary, let's see, Mary is pushing the cart. So technically, all right, if this is the horizontal, Mary is pushing the cart at a 55-degree angle with the horizontal. So Mary is pushing the cart with a vector that looks like this, all right, where this is 55 degrees. Meanwhile, Joseph is pulling the cot at a 40-degree angle. So if this is the horizontal, then Joseph is pulling the cart and this is the 40 degrees. All right, however, to find the resultant vector, having a pretty picture like this is not as helpful as having a chart. So draw yourself a chart like this one. So in this column, we'll just call it Mary, because this is where we will record the forces and vectors that Mary creates. And we will call this column Joseph, all right, for his vectors. And in the final column, we will have the resultant. Now, in the first row, we're just going to record the magnitude and the direction, all right? When I write R and theta, I'm talking about the magnitude and the direction. And in the second row, we're going to convert to component form, X and Y. Okay, now what I'm going to be doing is walking through this four-step process. So step 1 will be to determine the magnitude R and the direction theta for each vector. So let's do that now. Let's start with Mary. The problem says that Mary is pushing the cot with a force of 120 newtons at 55 degrees with the horizontal. Okay, so we need the magnitude and the direction. Well, the magnitude is just the 120 newtons. So let's go ahead and write that down. So the magnitude is 120 newtons. So now all I need is the direction. Now, they are giving us the direction this way, 55 degrees with the horizontal. Okay, now we're going to have to convert that to a standard position direction in the following way. So let's draw ourselves a little diagram. Okay, so Mary was pushing at an angle of 55 degrees with the horizontal. So Mary was pushing, so that vector was looking something like this. And this was 55 degrees, right? 55 degrees with the horizontal. However, this is not standard position. So for standard position, I'm going to take this vector and I'm going to move it. Maybe I can literally just click on it and move it. Okay, standard position, it has to start off from the origin. Okay, so this is where it would be. So now I need to understand what the angle is. So if this is 55 degrees over here, then that means this angle right here is also 55 degrees. All right, because these are called vertical angles. Vertical angles are equal. Okay, so basically now I've moved the vector for Mary's force into standard position, starting from the origin. So the actual direction that we mean when we talk about magnitude and direction on this chart is the direction that you get when you measure from the positive x-axis. So we need the angle theta that's measured counterclockwise from east. So what I'm going to have to do is subtract from 360. So theta should equal 360 minus the 55. What's that? So that's just going to be 305 degrees. That's the direction. So let's go ahead and record that. So the magnitude was 120 newtons. The direction is 305 degrees. All right, let's move on and talk about Joseph. We need the magnitude and direction of the force that Joseph is pushing with. So let's see, what does it say about Joseph? All right, Joseph is pulling with a force of 200 newtons at a 40-degree angle with the horizontal. So the magnitude is just going to be the 200 newtons. Now the direction we're going to get from the 40 degrees with the horizontal. So the direction will not be 40 degrees, just like it was not 55 degrees for Mary. We'll have to do a diagram and figure it out. So Joseph is pulling at a 40 degree angle with the horizontal. So that would be like this. So this is the 40 degrees. Wait a minute, did I say that the direction would not be 40 degrees? I meant to say, in this case, the direction will be 40 degrees. If he's pulling at a 40 degree angle, that is in the first quadrant. So this angle is the actual direction because this is the angle measured from the positive x-axis. So we don't have to do anything fancy for Joseph. We can just go ahead and say 40 degrees for the direction. Okay, so we have just completed step 1. Okay, so let's take a look back and see what we've done. So this is what we're doing. Step 1, we wanted to determine the magnitude and the direction for each vector. And as you can see, we have the magnitude and the direction for Mary and for Joseph, their forces. So what's the next step? Step 2, convert the magnitude and direction to component form x, y. And we'll do that using the little formula r cosine theta, comma, r sine theta for both vectors. So that's what we're going to do right now. We're going to convert these into component form. So it said r cosine theta, so that means the magnitude cosine the direction angle. All right, this is r cosine theta. And then r sine theta would be 120 sine 305. Okay, similarly for Joseph, I can find component form by doing 200 cosine theta, comma, 200 sine theta. So all we really need to do is put these expressions into our calculator. So when I do 120 cosine 305, I get 68.83. 120 sine 305 is negative 98.30. Got to round up. So there I have the component form for Mary's force. Let's do the same thing with Joseph. So this is what I get for the components of Joseph if I type those expressions into my calculator. So when I look at the component form for Joseph's pull, it looks like this. All right, let's see where we are in our series of steps. So we've just completed step 2. We converted the magnitude and direction into component form for both vectors using the little formula r cosine theta, r sine theta. Time for step 3. We will add the vectors to find the resultant vector in component form. So this is very simple. So we have these two vectors, okay, in component form. The resultant vector should be the sum of these two vectors. So of course I can get this resultant vector in component form by simply adding the corresponding components. So I've added the 68.83 with the 153.21, and that's how I got 222.04. I've added negative 98.30 plus 128.56, and that gave me 30.26. So this is the resultant vector in component form. And really that's why we converted from the form of the magnitude and direction that we were given. We converted them into component form just so that we could add them together easily like this. There's no way to directly add the vectors when all you have is magnitude and direction. But component form makes it easy. So that's the end of step 3. Now it's time for the fourth and final step. Determine the magnitude and direction of the resultant vector. Okay, so I have the component form, but what I don't have is the magnitude and the direction. So that's what I need to calculate now. Okay, so off to the side, let's calculate the magnitude first. Okay, so the magnitude of the resultant vector. We can get this by just using the magnitude formula. Okay, look at these components. So if I take 222.04 squared, and then I add 30.26 squared, and then I take the square root of all that, that should be the magnitude. I'm just going to put that in my calculator. So here I've typed it in my calculator. Boom! 224.09. That's the magnitude. Let's record it right here. 224.09 newtons. Okay, now let's find the direction. Now I'm going to find the direction down below here the same way I did when I found the direction for Mary's force and Joseph's force. I'm going to make a diagram. Okay, remember that this is the resultant vector in component form. I have found the magnitude. All I need now is the direction. So let's make a diagram using an x and y axis. So looking at these components, I have a positive 222.04 and a positive 30.26. That means right and up. So I'm dealing with a vector that is in the first quadrant. So I'm just going to go ahead and draw myself a vector into the first quadrant like this. And I will go ahead and make a triangle out of it surrounding the direction. All right, very often I have to put an R in here, called the reference angle, and often I have to subtract from 180 or add to 180 or subtract from 360. But if it's in the first quadrant, that's the one time that I don't have to subtract or add. I can just use the angle that I get. So anyways, the horizontal component goes here, 222.04. The vertical component goes here, 30.26. I can use this diagram to get the direction because the tangent of theta will equal 30.26 over 222.04. Therefore, the direction, angle theta, should equal the inverse tangent of this very fraction. So I'm just going to put this in my calculator and see what it is. So here I've typed it in my calculator. Bam! 7.76 degrees. And that is the direction. So I can go ahead and record that on my chart. All right, 7.76 degrees. Now, often I have to convert this to bearing or north of west or something like that, but in this case, I really don't have to do that. All right, this direction is very similar to the direction that Joseph was pulling. So we're just saying that whereas Joseph is pulling at an angle of 40 degrees with the horizontal, the resultant vector is 7.76 degrees with the horizontal. So I'll just add with the horizontal. So this box is really the final answer. We have the magnitude and the direction of the resulting force. Kabam! Put a nice box around it so you can clearly see this is the final answer. The Shanghai World Finance Center building in Shanghai, China was expected to be completed in 2001. That's some superfluous information for a vector problem. The building should be 1,508 feet tall. Also unnecessary to the problem. Suppose that a piling for this building is pushed by two bulldozers at exactly the same time. Now, from context, I'm trying to know what a piling is. Honey, what's a piling? It's like it's let the record reflect she indicated some type of a pole that's like a support. Okay, who wrote this problem? I don't like it on many levels. Anyway, so there's some type of a pole. It's being pushed by two bulldozers. And right about here is where the actual problem begins. In fact, let me put a little asterisk. Everything before this asterisk was a waste of time. One bulldozer exerts a force of 900 pounds in an easterly direction. So let this vector represent 900 pounds in an easterly direction. Now, another bulldozer exerts a force of 900 pounds. Wait, I already said that. The other bulldozer pushes the piling with a force of 2,150 pounds in a northerly direction. Well, you know what? I didn't leave myself enough room for that. So here, I'm going to put the 900 easterly vector here, and I will put the 2,150 pound northerly vector here. So, what is the magnitude of the resultant force upon the piling to the nearest 10 pounds? So the resultant force, if I add these vectors, would be drawn like this. And the magnitude can be found by using the magnitude formula. I'll do the square root of 900 squared plus 2,150 squared. I'll just put this in my calculator off camera. This magnitude turns out to be 2,330.77 pounds. But they said to the nearest 10 pounds. So if I round this to the nearest 10 pounds, I would just say 2,330 pounds. Alright, that's the magnitude of the resultant force. In what direction is the resulting force? Well, the direction should be measured counterclockwise from the east. So basically I just need theta. So we can find that by doing the tangent of theta, which should equal 2,150 over 900. So therefore theta should equal the inverse tangent of 2,150 over 900. So I'm just going to put that in my calculator off camera as well. So theta is equal to 67.29 degrees. That's the direction of the force resulting on the pylon. That's it for number 5. That was a lot easier than the previous problem. Hopefully the next problem will be more of a challenge. Hey guys, that's going to do it for this video. Go ahead and click over here to watch the next video, and click over here to subscribe. That way you'll get every new video delivered right to your home screen.